Can you tell before we finish? Now, one of the things that I've noticed that you guys have trouble with is analysis of the time complexity of short programs. This is actually in the title of the course, Analysis of Algorithms. And so let's look at how to analyze some of these really short programs. In every case, I'm going to assume that there's an integer count, which will be initialized to 0. And at the bottom of each code segment, I increment count. And so the actual value of count at the end is what we're looking for. However, we're only interested in the theta complexity of it, asymptotic complexity. So we'll start with the simplest one, and that is going from int I goes from 0 less than n, I plus plus. That's the absolutely simplest one. Incrementing the count, and the answer, it's obvious that it's theta of n. Now what I'm doing here is I'm going to write the equivalent integral in calculus. I'm going x then substitutes for I, and x runs from 0 to n, just like I runs from 0 to n. And this integral is n, which is of course theta of n, and that's the answer to the problem. Now let's look at what happens when we have nested loops. I goes from 0 to n, and j goes from 0 to I. Well, of course, if j goes from 0 to n, it's obviously n squared. But if j goes all the way to I, then what happens here? We can replace this by an integral where x goes from 0 to n, and then the variable y represents the continuous analog of j. Y goes from 0 to x, and then dy dx. And integrating this from the inside out, we get x equals 0 to n, and the integral from 0 to x of dy is x. So we substitute that. When we integrate, we get n squared over 2, which is clearly theta of n squared. So the fact that this only goes halfway is reflected by the 2 here, which is asymptotically irrelevant. All right, let's do something a bit more complicated on this side here. Let us suppose that we have and this is where, I hate to say it, but you people have always, most of you have done badly. It's almost like people are answering these problems at random. Please don't do that. Please try to learn the technique. All right, we start with a logarithmic outer loop and a linear inner, no, this is just a logarithmic loop, sorry. We're just going to do simple ones first. Just one loop. Okay, so I go through 1 to n, and I is doubled every time. Now the way to handle this is to make a substitution. We introduce an integer L, which is the base 2 logarithm of I. And then, of course, because the logarithm of 2i is adding 1, doubling the number adds 1 to the logarithm. So we have L plus 1 is the base 2 logarithm of 2 times I. Now, making the substitutions up here, we integrate, we start with L equals 0. L goes all the way to not n, but the base 2 logarithm of n. And L increments by 1 every time, adding count. Now what's the calculus analog of this? The continuous variable z will correspond to x. I'm sorry, will correspond to L. And so we have the integral dz, because L increments 1 at a time, all the way to the last value, which is taken approximately as the base 2 log of n. And this integral is simply the base 2 logarithm of n, which is theta of log n. So basically we have 2 logarithmic possibilities here, doubling every time, and of course this one we have every time. Let's see how that works. We start with I, starts it in, and keeps decreasing, halving it until it's above 0. Doesn't go beyond 0. And in order to solve this, we do the same substitution. L is log I, and then L starts from the top, which is log n, and it decrements all the way down, not to 0, but 1. And so decreasing each time. So using z as the continuous analog of L, z starts at 0, goes to log n, and then keeps going. So let's see now whether I made a mistake here. No, I didn't. This goes to 0 here. Yeah, I did. This is 0, and this is 1. So I got them backwards here. Because the log of 1 is 0. So I did get them backwards. Now, when we integrate that, we integrate log n, z equals 0 is dz. And of course, that integral, this is a constant here, so this integrates as log base 2n, which is theta of log n. Let's look at a couple of them that are considerably more complex. And these are the ones that people really have trouble with. We have I going from 0 to n, one at a time, and then j going from 1 to I, doubling every time. And then over here on the other side, we have I going from 0 to n, one at a time, and j going from I to n, doubling every time. These are similar looking, but they're different. And in both cases, you can say this is a linear time outer loop and a logarithmic time inner loop. That's true for both of these. So you could say both of them are O of n log n. But we want a theta answer. Now, for each of them, we'll do the same substitution. L is the logarithm of j. Now, once we do that, the outer loop is still indexed by I. I goes from 0 to n, I plus plus. The inner loop is now indexed by 0, and it stops at the base 2 logarithm of, not n, but I. Sorry about that. The base 2 logarithm of I. And so, we could think of that in terms of calculus. The outer integral is x going from 0 to n, so x is the continuous analog of I, and z is the continuous analog of L. So z runs from 0 to the log of x, and that's dz dx. Now I integrate that starting from the inside. The integral of this, of course, from 0 to log x, it's just log x. And that's integrated from 0 to n. Now when you integrate x log x, when you integrate log x, you get x log x. It's actually x log x minus x. However, the minus x doesn't matter. X log x minus x. And this second term makes no difference asymptotically. So the correct value is theta of n log n. All right, let's go over to this one now. We're using the same substitution. Now, we can see that when we make j equals I, we're doubling j every time. So we want to add 1 to the logarithm of j, so we substitute L to be log j. Now here we have the same outer loop, and the inner loop is indexed by L, and it begins, since j begins at I, L begins at log I. And since j doesn't go beyond n, L does not go beyond log n. And L increments by 1 every time. All right, now let's go up and try to see all the integrals here. I'm now replacing these by the analogous integrals. You're going to integrate, here's the continuous analog of I. X goes from 0 to n, that's the same as before. And z being the continuous analog of L. Z starts at log x and goes to log n. You see, it starts at log I, log n, so and then it's dc dx. Now, when we integrate that on the inside, the integral here, dc, since both x and n are constants on the inside, we simply get the difference between these two. And that is the integral value. Then we integrate that dx. Let's go over to here. Now, the integral with respect to x of log n is just x log n. The integral of log x, on the other hand, is x log x minus x. But we put a minus sign in front of that because of that minus sign there. Now that's integral from 0 to n. It's evaluated. Now what happens here? X becomes n, then it becomes 0. Well, the 0 part doesn't matter. And for n, we get n log n minus n log n, and then minus minus, which is plus n. And the answer is theta of n, which is the correct answer to the problem. Let's look at another more complicated example, one that gives you an answer of log n. All right, we'll start with I going from 2, and we're going to square it every time. So if I is set equal to I squared. And then we're going to do 2 substitutions. We're going to let j equals log I, and then we write the new code here. J starts at 1, it goes all the way up to log n, and have, it doubles every time. How did I make that mistake? J equals 2 times j. There we go. All right. Now, we let L be the log of j, and we start with L equals 0, because that's the log of 1, and L is less than the log of this, which is log n, and L increments by 1 every time. Well, whenever we have this increment by 1, we simply have the answer to be the difference between those two, which is log n. All right, now we can do it with square roots instead of squaring. It's really the same concept. So we'll start with I equals n, and we won't go any lower than 2, because we could get trapped. If we're at 1, the square root of 1 is 1 and 1, 1 forever. We'd never get out. So we're going to set I equal to the square root of I, and there is such a function that you have to call it in from whatever library in C++. Other languages have it built in sometimes. And once again, we set j to be the base 2 logarithm of I. Substituting j starts at the log of n, j goes to 1, which is the log of 2, and j equals j divided by 2, because the square root of I, the logarithm of the square root of a number, is half the logarithm of a number. All right, now continuing, we let a be the log of j. So L starts at the log of this, which is log n, and j, whoops, this is j, this is L, silly me. L is greater than or equal to 0, and L decrements by 1 every time. And then this clearly gives the answer. It's log n. I'll do a few more of these. Now, well, this one here, I have no explanation for, except that you have to memorize it. You start at n and you decrease by the log of n every time. Then it'll repeat log star n times. So you simply have to memorize this one. All right, now let's look at another one. Here, instead of I plus plus, I have I goes up by 2 every time. Turns out that doesn't matter asymptotically. Let's go through a formal description of it. If we let j equals I over 2 as a substitution, then j goes from 0. If I is 0, j is 0. If I is n, j is n over 2. So j less than n over 2 to j plus plus. And so it goes n over 2 times. But theta of n over 2 is the same as theta n. So that's the answer. Now this one is a much harder one here. Let's try this where we're going from 0 to n, but actually we're going to stop. We're going to test, instead of I being less than n, we say I squared is less than n. So the substitution we'll use here is of a different kind. We let n equal m squared. Then when we write I equals 0, I squared is less than m squared. But that's the same as saying I less than m. So when we get to this I equals 0, I less than m, I plus plus, the answer is clearly theta of m. But that's theta of the square root of n, because there we go. Finally, one that's really much harder. The answer is n to the 3 halves. We'll start with 0, go up to n, and then j, we'll start with 0, and then we'll go to j squared less than I, which is similar to this one here. All right, now, we're going to make a substitution, actually. We're going to just change the description. Instead of saying j squared is less than I, we're going to say j is less than the square root of I, which is the same condition. Now we write these as an integral. X goes from 0 to n, and y goes from 0 to the square root of x, dy dx. Now we integrate the inside. The integral of the inside is at the constant times the square root of x, so it's just the square root of x. And then we integral from 0 to n, integrate from 0 to n, and the antiderivative of the square root of x is 2/3 x to the 3 halves. We evaluate from 0 to n, and we get theta of n to the power of 3 halves.